Great. Welcome everybody to our usual weekly seminar. And it's a great pleasure to have today Richard Montgomery, who actually physically in Zurich, but since anyway we're broadcasting it to various other locations, we'll do it at slides and Zoom talk. And but for people who in Zurich, they can later catch Richard and ask more questions if they will not have opportunity to do it during his talk today. So he will talk about properly colored Hamilton cycles and the Bollobás-Erdős conjecture. Please, Richard.
Thank you very much, Benny. Thank you all for coming along, those of you in this building somewhere, as well as in China and elsewhere. So I'm going to talk today about properly colored Hamilton cycles and the Bollobás-Erdős conjecture, as Benny says. This is all joint work with Aleksa Milojević, Alexey Pokrovskiy, and Benny Sudakov. All of them are on this call. Okay, so let me start with the question of Dakin from 1976. He asked, is there some mu strictly bigger than zero such that any edge coloring of the complete n-vertex graph Kn with at most mu n edges of each color around each vertex has a properly colored Hamilton cycle? So I'll draw that for you. So what you're thinking of is a complete n-vertex graph. We're trying to avoid having a properly colored Hamilton cycle, and each vertex here, for example, has at most mu times n orange edges around it. And then I'm looking for a properly colored Hamilton cycle. So standard definition, no two edges which share a vertex have the same color. And in order to keep down some of the writing, what we do, well, I'll notate in just some edge coloring of the complete n-vertex graph Kn by Kn, and then put a C in the superscript to emphasize there's some coloring. And then say at most mu n edges of each color around each vertex, I'll say the maximum color degree, so delta Kn(C) is at most mu n. And then where I'm writing it, I'll just abbreviate properly colored Hamilton cycle by PCHC. So while I've been talking about this, hopefully it's given you a chance to think a little bit about this question. So this appeared in print in 1976. So it's a bit tricky, but it's not too challenging a question. So indeed, in 1976, there were two papers answering them. So in 1976 itself, two relatively short papers, 5 or 6 pages. This was answered by Bollobás and Erdős. He proved the answer is yes, using a value of mu, which was 1/69. And then it was also answered by Chen and Dakin, who naturally enough got the same answer of yes, but they proved this with mu being 1/17. And those were both in 1976. So the natural question here then is, what is the best value of mu? That we could have. And Bollobás and Erdős made a conjecture about what that value should be. So I'll write this down here. So Bollobás and Erdős conjecture. Okay, yeah, let me see it. I'll see their example first. So let's take, say, n to be 4k plus 1. Let's take two colors, red and blue. Let's take our n-vertex graph and color it arbitrarily, subject to this being 2k regular in red and in blue. Okay, so each vertex has 4k neighboring edges that I'm to color. And you can check if you wish. So we've chosen, it doesn't work with 4k plus 3. I want it to be 4k plus 1 so that I can actually do this and find this regular subgraph. Otherwise, the handshaking lemma will go wrong. Okay, so this has maximum color degree equal to 2n, sorry, 2k, which is the floor of n over 2. And it has no property colored Hamilton cycle. And why not? Simply because it has only 2 colors. So it has indeed no property colored odd cycle. Or any graph with chromatic number at least 3. And overall, we have n has an odd number of vertices. So based off this example, Bollobás and Erdős conjectured that this should be best possible, and they chose it for all n, this value. So this is Bollobás and Erdős in 76. They conjectured if the maximum color degree around each vertex is strictly less than n over 2, then there should be a property colored Hamilton cycle. Okay, so I think I've summarized this in the next slide, or recap this. Okay, so far we have this conjecture, Bollobás and Erdős. We have 2 bonds so far that was given by Bollobás and Erdős and Chen and Dakin. And we have this nice simple example due to Bollobás and Erdős. We have a regular 2 coloring that gives me an example for every n equal to 1 mod 4. So not very long after this was all in 1976. In 79, we have a slight improvement of Shearer. Okay, well, Shearer improved it by more than a factor of 2, so let me not say slight. So Shearer in 79 showed that 1/7 is good. And then after a bit of a gap, we have a result of, to 97, result of Allen and Guten, showing that mu can be taken to be 1 minus 1 over square root of 2, which I'll tell you is approximately 0.2929. So again, they more than doubled it. And perhaps actually more interestingly, okay, you have some improvements going on, but while studying a related question in 2011, Fujita and Magnant came up with another extremal example. So I'll draw that for you next. That I'll refer to as the tournament example. So how does this go? This time it's going to produce for us an extremal example to this conjecture of Bollobás and Erdős when we have an even number of vertices. I forgot to say at the start, I can see the chat. So as well as just interrupting me, if you have any questions, if you type something, I will possibly be able to see it. Okay. So let me just give you straight the construction. So take a regular tournament. So that means the in and out degree of every vertex is the same, and therefore it's very fixed. So regular tournament, I'll draw it here. Let's say it has, a regular tournament has to have an odd number of vertices. So let's say it has 2k plus 1 vertices, and each vertex therefore will have k out neighbors. and k in neighbors. And on top of this, take a new vertex, vertex V, and let's add it as a dominating vertex. So it has an edge directed towards everything else. And we'll have n is 4k plus 2. So the same number of vertices in this tournament. This is a tournament, not a coloring. So what's my coloring? I'll take
a... You mean 2k plus 2.
Oh, yeah, thank you. Oop, a little aggressive. Okay, exactly. So actually, this works for all even numbers, not just those 0 or 2 mod 4. So the coloring is, let's take this vertex set. We take the complete graph on the same vertex set as the tournament, and we'll color, and we will take distinct colors CV for each vertex in the tournament. So each vertex here has its own color. They're all different colors. And we'll color the edge UV with the color of the endpoint of its directed edge. So with the color associated with V, if the edge directed from UV is in the tournament. So again, I have 2 things to check for the extremal example. The first should be, what is my maximum color degree? And the color degree, if we look around a vertex up here, then all the edges that are directed out from W will have a different color, as they're the color of their neighboring vertex instead. So I only need to worry about the incoming edges for the color degree, and every vertex has k incoming edges in the original regular tournament, and then I added 1 vertex dominating everything. So the maximum degree is at k plus 1, which is equal to n over 2. Okay, so it has the degree, which is equal to the floor of n over 2 here. So it does hit this Bollobás-Erdős point. And does it have a properly colored Hamilton cycle? So this doesn't either, for a more interesting reason than the first case. And in order to see that, let's think about any properly colored cycle within this graph and think about the directions of its edges. Like this. Okay. So, and the simple thing is, so every edge has a direction in the tournament in a cycle. Let's complete this into a cycle. And 2 edges cannot be directed towards the same vertex, like so. Otherwise, they both have the same color next to that vertex. So that can never happen. And therefore, this is a directed cycle. So every properly colored cycle is a directed cycle. And I chose the original tournament, so the tournament T, so it has no directed Hamilton cycle. Indeed, it was some regular tournament, and then I added on some vertex here, which was directed to everything else. So these are not the colored edges, they're gray, they're uncolored. All the edges from V are directed outwards, so there can be no Hamilton cycle. There's no edge at all coming backwards into V. Okay, so this is a second extremal example we have, and is our tournament example. That was in 2011 by Fujita and Magnant. They're studying something, a related problem. I think okay, this is again my summary slide. I've just added this tournament example. And the next progress we had was by Alan Lowe. So Lowe didn't quite improve this mu by a factor of 2, but in his defense, that would have been impossible. So Lowe gave an asymptotic version of this. So he proved that any mu, which is strictly less than 1.5, is good. So in particular, you fix your mu, as long as you let n be sufficiently big, then this maximum degree condition being at most mu n is enough. Implies this for n large. And he also provided us with another extremal example, which again doesn't have a properly colored Hamilton cycle for a different reason. So here we go, I'll call it the bipartite example. It's going to be bipartite, as you might guess. We'll take two classes of vertices. This side and the left-hand side is going to be somehow the important one, A. So I'll put 2k plus 1 vertices in there. And the size of B is going to be chosen just to maximize this color degree. So it will have 2k vertices. And for each vertex in A, I will again choose a distinct color. From CV overall V in A. And we'll color, we will also choose some other distinct color C0. We'll color everything in A with C0. And for each vertex V in A, I will color every edge leading out from V into B with color CV. And while you're thinking why that doesn't have a properly colored Hamilton cycle, I'll confirm what's the maximum color degree. Maximum color degree is simply 2k. Every vertex on the left in A has 2k color C0 neighbors and 2k CV neighbors. So again, this is floor of n over 2.
Richard maybe says that in B you say rainbow color with all distinct colors.
Yeah. Let's color this arbitrarily. Yeah. And yeah, we shouldn't use any color. So I already chose CV color. So I think, yeah, as long as it doesn't necessarily need to be rainbow, it can be anything, but let's not reuse any CV colors. Actually, I think I can just do it completely arbitrarily because I've chosen these colors CV to be distinct. So each vertex so far has rainbow 2k plus 1 colors and has 2k minus 1 neighbors to go. So we'll do it arbitrarily. So this is going to be quite another general class of examples. And we've confirmed its color degree is 2k, which is floor of n over 2. So I haven't actually told you n is obviously 2k plus 1, 4k plus 1 here. So again, the same as the Bollobás-Erdős extremal example is 1 mod 4. And then it has no properly colored Hamilton cycle, Y. So any properly colored cycle has an even number of vertices in A. And let's find the pointer color. And to show that, just in all of the examples going forwards as well, there will be more than one to come. If you think about walking around this graph in a properly colored path, if I'm starting in B somewhere, and if I cross across into A, I'll have to use a, let's say, cross across to V. I'll use an edge of color CV, so I can't go directly back into A. I have to wait for a turn. I have to spend one more vertex in A and use this green edge, and then I'll be able to come back into B. And importantly, I have to therefore come back into B. So let's go down here. If I come across with this purple edge, I can't go straight back across. I have to stay with the green edge. And once I've stayed with the green edge, I can't use another green edge, so I've got to come straight back using some different color CV. So every properly colored cycle has an even number of vertices in A. And we've chosen A to have an odd number of vertices. So there's no properly colored Hamilton cycle. And this reason is definitely very different from the tournament reason, and is a bit more related to the original reason that came from the regular coloring. I think this should bring me up to, okay, here we go, my summary again. So we have an approximate version of this conjecture. What's next? There's nothing else to do. You should just prove it for large N. And that's what I'll talk about to you. So here's results of Aleksa, myself, Alexey and Benny, 25 plus. So we proved this for large N, so I'll just write it as long as N is large, and the maximum color degree is strictly less than the floor of N over 2, we do indeed get a properly colored Hamilton cycle. And I'll try and show you something about the proof of this. But before I do, here's another extremal example. I didn't actually explain to you. So in my ordering here, I started off with E1, E2, and then came to F1. So this is because this extremal example that Lou came up with is a part of a wider class of extremal examples. And I won't show you that wider class because it won't actually impact on proof in a meaningful way. I'll just show you the kind of other extreme in some sense. So this other extreme we call the tripartite example. And I'll call it F2. So it's hiding within some wider class of extremal examples you can discover on your own wish. So the tripartite example is tripartite. Let's take 4k plus 1 edges, vertices in A and 4k in B, and another set C, which will also have 4k vertices. And so therefore this is slightly more restrictive. So n is 12k plus 1. And I'll just take 3 colors this time and color everything across here with color C0. And I'll color half of the things within A and half of the things within B, the edges. This color C0. Take a color C1 and color these C1. And the other half C2. And then within here, it's nice if I color them with C1 and C2, but really I can do this arbitrarily. In some, let's say arbitrarily, just rainbow so that it won't affect the color degree. And then just like before, I have my 2 tasks to do. So here it's a little more subtle. So what have I said? Everything should have, for example, an A should have all of its edges across to B are color C0. Everything down to C is color C1. And then I should split between C1 and C0 to be regular in orange and regular in purple. So there will be 2k regular in both of them. Within B, I again want it to be split as evenly as possible. But now everything in B has one more purple neighbor than it does this blue color. So it won't be regular in the same thing. But this is a minor detail, and you can color this so that it again has maximum color degree to be the floor of n over 2, which is 6k. And then a similar observation to before, we have that any properly colored cycle has an even number of vertices in the union of A and B. And that's an odd number of vertices, so it's the contradiction. And therefore we have an extremal example. So that, again, with this having an even number of vertices in A union B, think about walking around on a properly colored path, start off in C, and this time there are a few different possibilities. So I'll maybe just run through a couple of them, but note that if I start off in C and go to A, I can't come straight back. My options are either to wait in A, or I can cross into B. And then we need to look at these different possibilities, which I won't run through for you now. But the 2 sort of basic things I might do are to start off in C, go into A, then into B, and back into C. This will give me a properly colored path. And I also could go into A, use a purple edge, and then come back into C. Or I could go into A and use an even number of edges by using some of these orange edges and come back. So, okay. So this is another extremal example, but it's really part of the class of those extremal example. It's using some parity condition, why we can't have a properly colored Hamilton cycle. But we're not quite done yet with these examples. So here's another more interesting variation compared to this one, which I'll call a hybrid example. So it's going to have some components of the previous ones. It's also going to be tripartite. So it'll have 3 sets, X, Y, and Z. Okay, and what's going to be important here is that I'm going to choose things so that X is strictly bigger than Z. In particular, I'm going to have that x is 2k plus 1. Z is going to be 2k. That matches what I just told you. Y is going to be parameterized differently. So y is going to be 2, let's say some ky plus 1. I will take distinct colors. So like before, we'll have some special color, C0. We'll also have a color for each vertex in Y and a color for each vertex in Z. I will color everything in X with this color C0. Then inside Y, I will again direct this as a regular tournament. So there'll be KY out neighbors and KY in neighbors here. And then for each Y, I will, similar to before, color every edge directed into Y with color CY, as well as all of the edges from Y to X. So that colors everything within Y and everything between X and Y. And then for Z, so the edges between Z and Y, for Z, I'll color CZ in this direction. And then from Z to C0, I'll color some of them CZ and some of them C0. Where my only aim is to do that coloring to reduce the maximum color degree as low as possible. And then within here, let's say this is arbitrary with new colors. Okay, and there's some condition. I don't want Y to be too large, otherwise this will go a bit wrong just with the color degrees. So let's say Y is comfortably smaller, say, than n/2. I think as long as it's just smaller than n/2, it should work. So here the drawing is a bit more complicated, so there are more things to check, so I won't check all of the things. But let me just point out for you, let's say, okay, well, the color degree of Y, as I've drawn it, it has 2k plus 1 neighbors in X, and it has ky neighbors in Y. So it has in total 2k plus 1 plus ky, and we have n equals 4k plus 2ky plus 2 vertices in total. So this is equal to n/2. And you can check all these things, and that you can color these these CZ, C0 edges correctly. So this claim you can get. That then has maximum color degree equal to n/2. And then we need to argue it has no property colored Hamilton cycle. So the key point here is that if you are a property colored cycle, so any property colored cycle has at least as many vertices in X as in, sorry, at least as many vertices in Z as in X. Okay. And we've done our construction so that Z has one fewer vertex than X. And again, if you've just seen this coloring, there are lots of things you might consider. But the key point is that this tournament example, the reasoning we used for it, means that as you're walking around in a properly colored path in this coloring, if you, let's say we'll start off in Z and go into X, but as soon as I go into Y, and I'm going with an edge of color CY, and the same logic means that I can't ever exit back into X. I have to exit into Z. Aha. Okay, so here again is my coloring for this, so I can have room to draw something like what I just said. So if I start off here with my edge of color Z, okay, so there's some behavior I'll maybe touch on in a moment about whether I stay in X immediately. Maybe I'll use a green edge because I'm trying to use up vertices in X. But after that, either I can go back into Z, but really what I want to do is to preserve, use as few vertices in Z as possible. So what happens if I go into Z, into Y? My next edge can't be this orange thing. So it must be a different color and it must be directed into that other thing. And just like before, you see this is going to be a directed path. Every time I arrive at some vertex Y prime, I won't be able to go back into X because all of these edges are, oops, the color of Y prime. So all of these edges are all color Y prime. So I can't go back into X. I'll have to go in, once I'm done using vertices in Y, I'll have to go into Z, maybe back to this vertex Z. So this is the typical pattern for, and just to give you one example, if I'm in Z, my sort of options look like if I am using a blue edge like I've drawn here. So actually I've done something illegal. I've come straight from Y into Z and then headed straight back out again on a CZ edge. So this is not good. So it works out that if I can use two consecutive vertices in X, this color C0 edge, then I must have arrived with the color CZ edge. So I can't have come directly from Y. I must have used another vertex in Z. And this is how you can argue that you must use at least as many vertices in Z as you do in X. So this is the end of the extremal examples. And maybe the key point about the proof of the theorem that I'll talk to you a little bit about in the remaining time is that even though this looks a bit crazy, in my opinion at least, it actually arises relatively naturally in the proof. It's complicated enough, I won't show you this. What instead I'll try to show you is how the tournament example arises from our proof. So we didn't just come up, we didn't just create this out of nowhere, we were trying to prove it. And then this example reveals itself. So here's the summary before I start talking about the proof a little bit more. This contains essentially everything I've said, but most notably, this is a theorem. I'll talk about the proof. We will have these. I showed you 5 different examples. The one to remember most is the tournament example, because I'll talk about that. Okay. So I'll talk now a little bit about the proof, as I say. And this is the result we'd like to prove. So our proof is by a stability analysis. Which is a relatively well-known concept, but just in case you haven't come across it before, this is where we're going to try to find, and we're really going to try to construct one, try to construct in some way a properly colored Hamilton cycle. And if we can't do this, so if what we're trying to do fails at any point, we will conclude we look like an extremal example. Okay, so this is a technique that has been used for quite a few extremal graph theory results. And it follows from the idea that we've come up with these different extremal examples, but it's not just those precise examples that we should be worried about. If I take one of these previous examples and just change the colors of a few edges, then it's still going to be pretty hard to find a properly colored Hamilton cycle. I'm going to have to really exactly use that edge, those few edges that I changed the color of. And what can I say about the proof? So the way we construct this, let's take a new slide so I don't run out of space. So we have some scheme in which to do our construction, which is going to go via some absorption, which if you have not come across before, I won't explain it because it won't matter. But the shape of what we're going to do, excellent. Okay, so constructing our properly colored Hamilton cycle takes 3 main components. And the first task is going to be to build an absorbing path. So I'll say some words which will mean something to you if you know about absorption, and if not, then it won't matter. So build an absorbing path P with a random vertex reservoir. Let's draw this down here. So somewhere within our properly colored path, somewhere in our edge-colored complete graph, we'll find this path, which can absorb any vertex set from some smaller random set R. And when I can't do this, we're going to look like one of 3 of the previous extremal examples, which were E2, which was the tournament, or the ones I called F1 and F2, which were the ones where I needed to use an even number of vertices from one subset, the bipartite and tripartite examples. And this is sort of a standard absorption approach if we first try and build this path. If this works, then we'll start off in task 2, where we cover the remaining vertices. If we take out those in the path and those in R, with some small number of properly colored paths. And if we can't do this, then it's going to look like this hybrid example, E4. And then, let me first draw this. So this is task 2. It's covered in some small number of paths. So our final task is then to join up these paths into a properly colored path. So we join the paths, including P, into a properly colored cycle using vertices in the reservoir. And if we can do that, then we'll apply the absorption property to get to a properly colored Hamilton cycle. And if we can't do this joining up, then we're going to look like the tournament, which was E2. So let me emphasize this makes a lot of sense on sort of some higher level. So the experiment examples we had didn't have a properly colored Hamilton cycle for different reasons. For example, the tournament, what was I really struggling to do? I was struggling to walk around in the tournament with paths, the directed paths. I was being forced to use certain edges as my next edges. I'll talk a little bit more about that in a second. So because of that tournament example, it's really hard to join two edges by a properly colored path because of this walking behavior. For task 2, the hybrid example, it comes with a sort of a space condition where I was struggling to use vertices in X without using vertices in Z. So even if I give you a small number of properly colored paths, then that's going to be difficult if we're close to that example, but I've altered it so that Z is much smaller than X, or significantly smaller by some X. So there's going to be some behavior going on. The smaller Z is, the more paths I would need to be able to cover everything in X. And then for task 1, this tournament example, that just comes up from creating small absorbing paths and trying to connect them together. So the main real ones are F1 and F2. And in F1 and F2, I was always arguing that it covers an even number of vertices from some set. So I'd really struggle to absorb one vertex, for example. So that's going to be how that comes up. Okay, so I'll just take in the last moment and say, for the tournament example, that comes up. So the third task, the meat of it, is if I have an edge xy and a different edge zt, it's really convenient if I can join these into a properly colored path in some manner. Okay, and I'm not just joining vertices together because I need to remember to be able to join eventually up into this properly colored cycle. So I want to remember what color I'm coming from. So suppose this is not possible. So suppose I can't do this. And then the key point here is if I walk in a properly colored path from xy, so like so. So from xy, I'll walk in properly colored paths. and orient the edges in the direction that we walk. So from the first edge xy, my color degree is at most n over 2. So there are going to be n over 2 possible edges which are not blue, which I could walk to. So I'll direct them all out from y. And I finished, so let's just say that this is going to give a direction that's close to being a tournament, because if it turns out that I've directed, say, this edge in 2 directions, then it means I can arrive as a properly colored path on both sides at some w. And this means that I can have a properly colored path from xy into z, which finishes in 2 different colors. And this is really helpful because if you could do that as well from zt to some w prime, then it doesn't matter what color w prime is, you can find a properly colored path between those 2. So this is just an example of how the tournament sort of coloring arises, and the others also arise in a similar way. And then I'll leave you with the following slide, so it just talks about extensions and questions. So you might think about, we have this result, but what about in hypergraphs and in non-complete graphs? And the summary of this slide is both to recommend this recent paper of Antonek, Kamchev, and Rychinsky, which gives an overview of this. But the key point here is that the original result of Bollobás-Erdős and Chen and Dakin is known in hypergraphs and in non-complete graphs. But in both cases, it'd be interesting to know what the best possible value of mu is in these 2 results. So thank you very much for your attention. That's all I have.
Okay, so thank you very much, Richard, for a great talk. Right, so it's now open for question. Please ask questions.
Hi, Richard. I have a question. I'm very interested in this problem, and actually I've worked on it for several years. So my question is, I know that Goutin and Kim have a conjecture about the algorithm complexity of finding a properly colored Hamilton cycle in edge color complete graph. So they conjecture that it should be polynomial to determine whether a edge color complete graph has a PC properly colored Hamilton cycle. So I mean that by your proof, can you just show that by a corollary the conjecture is true or not?
Definitely not as a corollary. If nothing else, so as written, the part of the argument that we're using where we're covering most of the vertices with few properly colored paths is written as some maximization. Whether that can be done algorithmically, I don't know. I haven't thought through all of the details. I suspect that's would be the most challenging part of using it. So it seems very complicated. I don't know much about the complexity, but having to recognize whether you're close to the colorings and then study the colorings in total to really get a proof of it seems very difficult to me.
Yeah. Okay. Thank you. And I like to comment that I didn't expect there was so many. You give 5 examples, extremal examples.
Yeah.
Before I only realized like 2 or 3, at most 3, I think. and what we have done is a little bit related to we prove that if the graph is monochromatic triangle free, then everything is fine. And also the algorithm conjecture is true, but I don't know how to do more based on the triangle free conditions. So that's where I start for this question. Okay, thank you. Yeah.
So actually, my comment, maybe you can send us your preprint so that we will know right, what is there. Right.
Sorry?
So maybe you can send us the link to your preprint or to your paper so that we can look and know what is there.
Yeah, okay, of course. It's no problem.
Thank you very much.
Thank you.
More questions?
Hey, Richard. Can you hear me?
Yes, I can hear you.
Okay, thank you. Yeah, very nice talk. Yeah, so I have probably a very strange question. How, like, it seems to me there are many steps here, and it's like in every step you either get something or you're close to some extreme example. And one question is, would you able to show that indeed if the max degree is n over, like, not smaller than this threshold, but if it's exactly n over 2, and either you arrive at one of the extreme examples, or you can find a Hamilton cycle, rainbow Hamilton, properly colored Hamilton cycle.
Yeah, this is something we've discussed. I think it should be doable. Definitely, our proof is really identifies these extreme examples, and I don't think there are any other ones. Whether it can be nicely written down into one, I don't know.
Okay, thank you. The other thing is, like, when you find such, like, when you're working on this, how, like, is there some indication that certain things will work out, or like it feels to me that, sorry?
I don't quite know how it does. I mean, I can say that it's quite a long proof and a complicated proof in some aspects. But at the same point, it is a very it just involves it's very sustained. There's no part of it that's really very difficult as written down, like more difficult than the rest of it. Some bits are more difficult to realize what the behavior is, but a lot of it is just being very consistently calm and logical about what is going on and what arises. And so we were trying to prove it via the sort of tasks that I laid out. And then the extreme examples really do appear relatively naturally as sort of obstacles to what you're trying to do.
Okay. Yeah, thank you.
More questions?
Maybe one final question from me. You were mentioning this work of Dudek, Fries, and Ruchinsky on hypergraphs. Is there any conjecture for what the threshold should be for hypergraphs, what this optimal mu is?
I looked at their paper and I couldn't see any. So and I don't have any good idea for what it should be. For the second question, it should be a quarter, I believe. So it should be the same examples, but deleting half of the edges at random.
Okay, thanks.
More questions? So if not, thank you, Richard, again. Very nice talk. And thank you, everybody, for coming. So I hope to see you all next week. So we have 2 more seminars to go. Actually, I tell you the speakers. So the next week, it would be Andrei Kupavsky, and he will talk about spread approximation and application to extremal intersection problems, if I'm not mistaken. And the week after that, to conclude our program for this spring semester, would be no Galon. And thanks to Rugier, who already updated the webpage of the seminar, you can see both talks. And obviously, I will send the announcement soon. So I think we can stop the recording.